Good day, everybody. Good day, dear committee of the ICA 2026 of the 9th International Conference of Computer Science, Engineering and Education Applications. My name is Mihaila Vernik, and I represent the paper of Hybrid Quantum Classical Framework for Computational Mental Energy from Multi-Channel EEG Streams, with two other researchers, Lyubov Lещенко and Jibin Hu. Introduction. On the side, you can see the system design of the EEG end-to-end real workflow, which goes from acquiring signals to enabling timely actions, and used for a Asana 4-channel EEG and fMRI experimental setup. The purpose of this research is to demonstrate that a unified quantum classical EEG processing pipeline can produce a standardized reproducible cognitive state indicator SME, computational mental energy, with measurable improvements in flow state estimation, stability, and computational resource efficiency, which was validated through the real EEG recording across 8 cognitive activities and executed on the real IBM quantum hardware, like IBM Marrakesh. And moreover, this paper aims to show that the hybrid quantum classical inference reduces flow probability prediction variance by over 40% using Pearson correlation, which shows 0.86 between ideal, similar, and real quantum hardware. The SME framework captures dynamics difference between high demand and low demand activities. Problem statement. Given a stream of time-stamped multi-channel EEG windows, WK, the task is to estimate a robust window-level cognitive state indicator suitable for online monitoring and aggregation over sessions. The input consists of multi-channel G spectral powers, organized by frequency bands and channels. A task complexity indicator, C, function dependent from T, which lies in range from 0 to 1 included, a signal quality indicator, Q, and configurable runtime constraints, including shot counts S, circuit depth D, and latency matched. The expected outputs are a flow state probability, P-flow, and window level value computation mental energy, and session level, which aggregates the total amount of windows during this session, flow share, and the longest flow streak. The system must operate under streaming conditions with bound latency, maintain reproducible feature engineering and model interfaces, and support resource-aware adaptation for QPUR simulator backends. 4 main contributions were made during this paper and research. First of all, it's computational mental energy. This is a window session-level cognitive indicator with an explicit unit in Vernix. And Vernix is the unit introduced in this domain and this work, which actually represents a microvolt square multiplied by second. Or in other words, it's time integral of the squared EEG amplitude over an observation window, delta. Next is going to be a hybrid quantum classical inference. We will use 4 qubits and VQC with a classical LMLP using a fusion function mu. Third is going to be resource-aware meteoristic optimization, which uses 4 primary algorithms like PSO or unculling optimization, for model parameter optimization shots, and depths against quality and costs. And final, fourth, deployment streaming architecture. We'll have a variable device which goes to the streaming device like Raspberry Pi or any computer server with quantum inference and hybrid or classical backends to compute SME formalism. For the methodology, we'll start off with the window definition. So as an example, we have window of each action like reading or doing something at 5 seconds, which is actually the best amount of time used for the calculation of Fourier powered spectral band using Welch method. And next one we'll use band power with weights for the delta, theta, alpha, beta, and gamma specifically. And actually we'll be interested in those 3, theta, alpha, and beta mostly, since in some of the devices gamma might not be included, so that it will be zeroed. And compute the total sum of this. Next, we'll have reduced quantum input. So we'll have our spectral powers, frontal asymmetry using alpha. Next, we use engagement, beta divided by theta, and complexity of the task. And it also forms a vector of 8 features. To compute p-flow on the quantum machine, we'll use measurements, like sum of measurements of the count of m, and divided by number of shots. And finally, 1 Vn equals to 1 microvolt square second. Next, we'll have a modulation function, which uses 3 lambda coefficient for the complex function and p for probability. To compute SME rate, which will be in Wernicks per second units, and it's k, it's a scalability coefficient multiplied by power band, energy power band multiplied by modulation function. And if we want to compute the rate, the compute window level, like what was during this window, we should multiply by window size, as example 5 seconds. And to compute for a session, like reading for 1 hour, there's going to be a sum of those window level. One more note about optional approximation we're using C-mapping. Since we're using the EEG device, we can compute impedance on the electrode and divide it on NCME divided by it. So with that, we'll have ohms, like skin has around 10k ohms, and then we'll have approximation in joules. Next, for the quantum. For qubit, we'll have our VQC. So first of all, we'll do the axis for plotting, rotation on right and RZ on these steps. Next, we will do some feature instructions using RZ entanglement on this layer. There's going to be a second layer. On third layer, we'll use entanglement CNOT. And finally, we'll use some to trainable parameters theta and phi. And we will use two more the same layers for trainability. For the classical neural network, we will use a simple feed-forward. So we'll have 22 features, 4 bands multiplied by 5. It's going to be 20 bands plus complexity plus quality of the signal. Next, we'll have 64 layers of ReLU with activation function 32 and 1 sigmoid for the final computation. The fusion function will be with quantum branch, classical branch, and fusion weight 0 to 1. As an example, if we use 1, then we'll be using only quantum backend for this. And we'll use this hybrid. 0, then we'll be using classical. If we're using 0.6, it's going to be hybrid. Actually, from the experimental setup, 0.6 provides best results. Methodology. So on left image, we'll have end-to-end architecture with real-time speed computation with hybrid quantum classical inference and synchronous persistence. We're starting from the EEG using streaming node, sending a raw data to server, segmenting the data, preprocessing signals and normalizing it. Then we move into spectral feature extractions, like 8 or 22 features. We build in a vector. Then we deciding where should we start, execute on a quantum service or a classical network service. After executing, we will compute the computational mental energy and send it to the dashboard. In parallel, we save the database, update the session features, and use meta-heuristic for the parameter optimization. For the window execution sequence for online SME estimation and continuous optimization. As an example, if we start from once we computed the powers and indices, we built this vector, and then we run, then we compute SME rate. Then we have a threshold like 0.85 or 85% of p-flow, which if it was detected. Update, save, and then we do background optimization using theta, shots, and depths, and update in the quantum scheme. Research results. So in the figure 7, we show the dependency between SME rate and task complexity. If we start from a simple task like resting and going up to the cardinal or mass problem solving, the difference or dependency is linear, correlation between them. For the Results extrapolated by SME budget on a daily. Like as an example, if I was only doing during the day resting with my eyes closed, it would take around 136,000 VNs per day. It's approximation, please note. An example of coding, it's going to be for 2.5 million VNs per day. But to keep this whole day, it's going to be a challenge. Since this is extrapolated result, if me or someone, a human, will be doing this during the whole day, this operation. That's quite a lot. Next, we'll have a comparison of VQC performed leveraging quantum circuit performed on Real Simulator and IBM Microresh. So as an example, here, of course, execution will be different because of Q. Circuit depths, streaks. And next, we'll have quantum model accuracy. So on a simulator, it's a bit lower, but in reality, trained parameters should be trained on much more complex data and much more available than in its current setup. Current setup had only 20 hours of recordings. Next, we'll have p-flow definition. So it shows iris simulation almost similar to the IBM Kingston. But in reality, with more data, the difference will be significant. So IBM Kingston should be much more, or Microresh will be much more precise. And final table of results. As an example, if we subjectively select the complexity of each task from 0 to 1, then we'll have some VNs like resting, it's going to be 37, Vernix per second, browsing 110, 12, email or you're watching YouTube, TikTok 130, reading general 150, reading technical almost 200, debugging coding 300. So difference is almost 10x or 9x. All those parameters are actually dependent from person to person. Discussion. Introduction of Wernicke unit further provides a common scale for comparing SME values across sessions, devices, and subjects, analogous to how C conventions standardize physical measurements. The activity-dependent consumption analysis and the restoration depletion model first demonstrates that SME is not merely a momentary index, but a framework capable of capturing the temporal dynamics of cognitive resource management across task sessions and multi-day schedules. There are also several limitations. Should be noted, the present paper emphasizes system formalization and work combinational examples. Large-scale comparative experimental evidences across subjects and task domains should be expanded in the future submissions. And the conclusions. This paper has presented a unified framework for real EEG-based cognitive state assessment centered on a new operation indicator, computational mental energy, SME, measured in the Wernicke units. The system combines multi-channel spectral feature extraction, a 4-qubit rational quantum classifier, and based on the data that we're using on 2 layers of reuploading, and with heuristic resource over optimization within deployment-ready streaming architecture. We'll have 3 inference models, quantum-only, classical, and hybrid, only supported without modifying the SME combinational core. A working example has demonstrated end-to-end combinational consistency from raw EEG band power to a window-level SME value. SME formalism with Wernicke unit produces extrapolated daily budget of approximately 7.6 million Wernicks across 8 cognitive activities measured with Mu-Susena headband and execution on real IBM Microresh 156 Heron 2 quantum processor confirms that the system is ready for deployment on currently available quantum hardware. The future work will focus on subject and empirical validation with larger cohorts against established engagements, and this is richer subject-specific adaptations through transfer learning, formal calibration protocols, ground and psychometric scales, VQC retraining with activity-specific labeling execution, additional IBM quantum hardware. And we should validate the SME balance between restoration model across the different population and sleep conditions. Thank you for your attention. Questions?